This counting ticker forms one of the simplest possible sequences describable by mathematics. It's a linear sequence that increases by 1 at every step, the initial value being equal to 1. If we number the order of every item in the sequence, we understand that the whole thing is generally described as the term value being equal to the term number. The reason it's called a linear sequence is that, when graphed on the standard Cartesian coordinate axis, it clearly forms a line. But since a line with a different gradient and vertical offset is still a line, we can further generalize the sequence as t sub n equals an plus b. By the way, if you've ever seen this form of a linear sequence, it's actually just the same thing, just reorganized a bit to make it easier to work with in certain contexts. For the sake of keeping our expressions clean, I'll use the first form, but just know that either one is correct. Arguably the next simplest sequence of a higher complexity than the linear sequence is a quadratic sequence. The sequence 1, 4, 9, 16, 25 can be paired with its term numbers, and we evidently see that each term value is just the square of the term number. Though, if we wanted to be more general, as we were with linear sequences, we could actually write it like this. This is the general form of a quadratic sequence. But why is it called quadratic? If you're as into words as I am, you'd probably assume that because n is squared in the first term of the polynomial, the quad in quadratic is related to quadrilateral or something, as in square. That's not a far off guess. It comes from the French quadratique, which itself comes from the Latin quadratus, used to describe a square number in the context of mathematics. Okay, so this is linear and this is quadratic. But what if we combine them? Let's take the linear sequence and nudge it into the quadratic, replacing all occurrences of the quadratic's n with an entire linear sequence. And let's just clean up those name constants so they're all unique. There we go. We now have a linear sequence inside a quadratic sequence. What is this called? Well, if we simplify it, we could obviously just call it another quadratic sequence, but that's kind of missing the point. I want to encapsulate and describe the idea of nesting sequences inside one another in a simple way, and throughout this video, I hope to develop a language to help us do so. Before we get into my own work, I'll just recap some common types of sequences in case you haven't been to school in a while or you didn't study mathematics or something. We've already covered linear and quadratic sequences, but there are many others out there. In fact, there are innumerably many possible sequences since polynomials can be infinitely added to. For example, we have cubic sequences, so called because they're based on cubic numbers. Quartic sequences, so called because they're based on polynomials containing the fourth power. By the way, it's such a missed opportunity that they decided to call it quartic instead of hypercubic, but I digress. Similarly, quintic sequences are just sequences based on polynomials containing the fifth power. There's no point going beyond these 5 sequences for our purposes, but just know that we could go further if we wanted. The other kind of sequence you probably learned in school is the geometric sequence, also known as a geometric progression. In a linear sequence, every next element is the previous element incremented by a fixed amount. In a geometric sequence, every next element is multiplied instead. So, something like 1, 2, 4, 8, 16 is obviously a geometric sequence, because it's very clear that you just multiply the last element by 2 to get what comes next. Here we see that the common ratio is 2, and the starting value is 1. If we want to generalize this, we can write it as the initial value divided by the common ratio multiplied by the common ratio the term number of times, as to account for the first term not being multiplied for this ratio. Written mathematically, we get t sub n equals a times b to the n, where a is the initial value divided by the common ratio and b is the common ratio. In the alternative form mentioned earlier, it looks like this. The term geometric sequence has a more complicated etymology than linear and quadratic sequences, but as far as I could find, it's related to geometric means and triangular figures that can represent repeated multiplication of a common ratio, as shown in the stack exchange answer by David K. As a side note, while investigating this etymology, I found out that geometry actually comes from geometry, meaning measurement of the earth, which is pretty obvious looking back, but you learn something new every day. Anyway, the next type of sequence is a harmonic sequence, which is really just the same as a linear sequence, except every item in the sequence is reciprocated. Since we know that the general form of a linear sequence is t sub n equals a n plus b, we can just say that the general form of a harmonic sequence is the reciprocal of that, or t sub n equals 1 over a n plus b. While you probably didn't learn this kind of sequence in school, it actually does have some pretty cool applications, such as stacking blocks on top of one another in an optimal way, which is based on the sums of harmonic sequences called harmonic series. Besides the harmonic sequence, we can also modify a linear sequence in another way. Instead of using reciprocation, we can use factorials. So every term in a linear sequence, like 1, 2, 3, 4, 5, can be factorialized, factorialificated. What's the verb form of factorial? Leave it in the comments if you know. To get 1, 2, 6, 24, 120. So the general form of this particular sequence would be t sub n equals n factorial. And if we wanted to generalize it further to any kind of factorial sequence with any vertical offset, we could make it t sub n equals a times b n factorial plus c. The last commonly known kind of sequence I'll cover is the Fibonacci sequence. The previous sequences have all been deductive definitions, meaning we could just arbitrarily get any term in the sequence, if the free variables are all given a value, by substituting their n for an integer term number. Unlike those, the Fibonacci sequence is inductive, meaning that it depends on knowing the values of previous terms. If you haven't seen it before, the Fibonacci sequence is derived by adding the previous two terms to create the next term. So 1, 1, 2, 3, 5, 8, 13 is a Fibonacci sequence. Look, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, and so on. Computing Fibonacci numbers is a common programming task, and it's pretty unique amongst our current sequences due to being inductive. For term numbers above 2, we can write it as t sub n equals t sub n minus 1 plus t sub n minus 2. And while people don't usually generalize it beyond that, we could easily imagine doing so by throwing in some free variable coefficients and adding another value, though we won't be doing this. Finally, before we move on to the next part of the video, I'd also like to coin two other kinds of sequences. These aren't commonly recognized, and I haven't seen anyone use them as sequences, but I'll still define them for the sake of giving us more kinds of sequences to play with. So, a sinusoidal sequence is a sequence based on a sine curve, and a cosinusoidal sequence is one based on a cosine curve. We can generalize them according to all the properties of a sine model: the period, amplitude, vertical offset, and horizontal offset. The sequence of this kind based on a sine shall be called sinusoidal, and the one based on a cosine shall be called cosinusoidal. Thus, for example, the sequence 0, 1, 0, minus 1, 0 is defined by the general term t sub n equals sine of pi over 2 n. Finally, we arrive at the point of the video. How do we combine sequences to make new ones? How would we describe them? How would we name them? Well, I want to talk about nested sequences. I touched on this in the introduction, but allow me to elaborate. First, let's take a quadratic sequence. The right-hand side here defines the term value of the nth term. What we would really want to do with this is to chain another sequence, for example, a linear sequence into the quadratic. A possible way to do this is to compute the sequence for the linear sequence, and then use the output from the linear sequence to feed into the n values for the quadratic sequence. What do I mean? Let's try a small example. Take the linear sequence t sub n equals 2n plus 1 and calculate the first three terms for n equals 1, n equals 2, and n equals 3. You get 3, 5, and 7. Then take the quadratic sequence t sub n equals n squared plus 2n and calculate its value for n equals 3, n equals 5, and n equals 7. You get 15, 35, and 63. Isn't that cool? We're basically using the linear sequence to generate which terms we pick out of the quadratic sequence. I think this is one of the most interesting consequences of nesting sequences, the ability to mathematically select for only certain elements of a progression. If we were to write this idea out in mathematical notation, we just replace the ends of the outer sequence with the selection sequence. Note that the variables of the inner linear sequence are the same in both cases, but there's not necessarily any requirement for them to be. We could just as easily write this, but we would lose the selection property of the inner sequence. Going forward, I'll actually do this, but just remember that the selection property is only maintained as long as the inner variables at each level of nesting are equivalent. Alright, let's try something a bit more involved. I present 3 levels of nesting. This is the general form of a linear sequence, nested inside a geometric sequence, nested inside a factorial sequence. My viewers are smart people, so I trust that you already understand the chaining of sequences into each other. Instead, I'll talk about the second question I asked in this section. How would we describe this sequence? To start, we definitely don't want to call it a linear sequence nested inside a geometric sequence nested inside a factorial sequence, because that's such a mouthful that it makes talking about this potentially interesting idea a complete hemorrhoid. I think the simplest solution is to write nested sequences out in function form. So our general sequence would be a of g of L of n, where a is a factorial sequence, g is geometric, and L is linear. This denotes a factorial sequence composed of geometric sequences of linear sequences of n, though actually now that I think about it, we can simplify this even further. First of all, obviously the innermost sequence will be in terms of n, so we could just drop that since it's implicit. Secondly, there's no real reason to write out the parentheses, since they don't really tell us anything like they would in usual mathematical notation. consideration. Hence, we arrive at what I call the letter form of our nested sequence. Great, we have a way to concisely describe nested sequences, but that's only half the battle. I don't know about you, but I actually like having names to describe the properties of sequences. The fact that it's a quadratic instead of just a Q, or a linear instead of an L, just feels more descriptive. What we also need then is an arbitrary way to convert letter forms to descriptive names. There are a few ways to go about this, but I actually think our simplified letter forms will be instrumental. See, any letter in the letter form can only take one of three positions. Either it's at the beginning, the middle, or the end of the letter form. This means we can assign a corresponding prefix, infix, and postfix to each type of sequence, and just replace each letter of a letter form as we go through it. But how do we get these pre, in, and postfixes? Ultimately, it's kind of arbitrary, but I decided to go through each kind of sequence under consideration and pull out some stuff from the start, middle, and end of their names, and using this method, arrived at the following table. Let's try applying this to the sequences we were looking at earlier, QL and AGL. Going through QL, we replace the Q with the prefix quadri, and the L with the postfix near. So, linear sequences nested inside a quadratic sequence can be called quadrinear sequences. Alright, let's try AGL. First, the A is replaced by the prefix facto, then the G is replaced by the infix metri, and finally, the L is replaced by the postfix near. So, a linear sequence inside a geometric sequence inside a factorial sequence can be called factometrilinear. But what's the point of this? At the end of the day, if this was actually useful in mathematics, mathematicians would have already invented it, or something similar. I just think it's a great deal of fun to come up with naming systems because I'm that particular kind of person. But speaking of systematizing things, don't you think there's some automation to squeeze out of this whole naming thing? Some years ago, when I first thought about nested sequences while sitting in class, wondering how they might be named and described, what properties they'd have, etc., I threw together some code to automate the naming of letter forms and to output HTML that would show the general forms of inputted nested sequences. Recently, I rewrote the code, changing some of the naming schemes and adding more sequence types, and I published it on my website, tirmid.net. Actually, that's what put the idea in my head to make a video about these quote-unquote cursed sequences. I'll keep how it works short, since you probably don't care about the code. On the off chance you do, it's like 130 lines of code, so I'm sure you can figure it out from the source. But in short, whenever this text block containing an input letter form is updated, this function is called. It generates both the name of the sequence and something I call the tech of the sequence. Don't ask why it's called that, I genuinely don't remember. This is a hangover from the earlier version of the program I made years ago. The tech is just a simplified formula that allows substitution with three variables and subscript and superscript formatting tags. It's converted using the tech to formula function to a user-facing general formula for the sequence, and finally written to the page. If you use the sequence inventor, you'll notice there's something called only significant. This just removes the free variables from showing in the formula, so that you can better see complicated combinations whenever having a lot of free variables clutter things up a lot. Got it? Good. Now we move on to my favorite part of the video, a selection of some choice nested sequences and their names. Once again, if you'd like to try this for yourself, check out the sequence inventor on my website. Linetric, quintici, harmotorial, cubintic, cubintimonic, cubintimonitorial, cubintimonic-torchi, sinusoidic, sinucoidic, geosortic, orthomonic, Linecci. Another thing I had a lot of fun with was spelling English words and seeing what kind of sequences they yield. Since only these letters are supported in letter forms, we are limited in our choices, but there are still a few good possibilities. For example, harmoctonenier, quadritintinenier, orthomonic, geoctotric, sinuctortinier, factosoidic, linocortic, and I'm sure there are more combinations, but these are just some of the best ones I've found. So, what was the point of this mental exercise? In all honesty, there really wasn't any, apart from the fact that it was a mental exercise. Hopefully this got you to think a bit about how we name things, how we might design linguistic conventions, or something to that effect. Thanks to everybody who's been supporting my channel as of late. I'm very happy with the growth we've been seeing, and as always, that'll be all.